So what is temporal locality and how can it help us implement a replacement policy for a cache? So to understand that, let's go back to the cache example that we used before. So I have a tag array and a data array populated with 4 addresses. Now let's take a look at the address pattern that may have resulted in this cache state. Maybe I access 31, then 10, 20, and 0. Now let me continue this a little bit more. 10, 20, 0, 20, 0, 20, 0. Now let's say I end up with a new address, let's say 7. Now the address 7 is not present in the cache, so it would be a cache miss. So I would go to the main memory and get the data. Now I need to find space for this address 7 in my cache. Now the question is, which address do I pick as a victim and evict it? Try to pause the video here and try to see if you can come up with a good guess for which address might be a good candidate as a victim. If you pick 31, that is a very good guess. Well, why does it make sense? Well, what you're intuitively using is this idea of a temporal locality. So what temporal locality means is if I access an address now, that address has a very high chance of being accessed in the near future compared to all the other addresses. So by that principle, I could argue that at this point, when I had to find a victim for the address 7, among the 4 choices I had, 0 had the highest chance of getting accessed in the future, followed by the address 20, and then followed by the address 10, followed by the address 4. So address 31 happened to be the least recently used address, and therefore, according to temporal locality, it had the least chance of being accessed in the near future compared to the rest of the 3 addresses. So I would pick 31 as a victim, evict it from the cache, and replace it with address 7 and its data. Now let's say I get another new address 8. Now 31 is out of the cache, so it is out of the picture. Now these numbers would change after I have brought in 7. So 7 would be the most recently used address, 0 would be the second most recently used address, 20 would be the third most recently used address, and now 10 would be the least recently used address, and therefore I would have to pick 10 as a victim and replace it with the address 8. Alright, so to formalize the notion of temporal locality, we can look at the precise definition of it. It essentially says that if you access a memory location, let's say 1000, you're more likely to re-access that location than you will be to reference any other random location. So according to this principle, if I access any new location that is not there in the cache, meaning the address is a miss in the cache, then temporal locality mandates that I evict some candidate from the cache and allocate this address that I just missed in the cache. And we also talked about the idea of a LRU, which is essentially that in order to realize the temporal locality, I should design a replacement policy which always picks the least recently referenced or least recently used cache block and evict that to make space for the new line. Is LRU an optimal replacement policy? Answer is clearly no. It's just a heuristic that works in the common case, but there can always be some program for which LRU is not the best replacement policy. Now the question is there anything like an optimal replacement policy? Well, unfortunately no, because we really don't know what a given program can access in the near future. If you can have the exact sequence of memory accesses that a program is going to make, then it is possible to design an optimal replacement policy. But unfortunately, in the real world, it's often impossible to predict exactly what sequence of addresses that a program would access going forward. As a result, there is no optimal replacement policy, and so we have to think about heuristics such as LRU to design a replacement policy.